Welcome. Here's the first script that I will be showing, which should be demonstrating what we've discussed on the lecture about open quantum systems. So far we'll be discussing only closed systems, something very specific, that is wavefunction description of an open quantum of a closed quantum system. So this script I have written for Octave, but I'm using a commercial version of that software, MATLAB, or it's a commercial version of the same language. It's a MATLAB. It has an editor which can highlight syntax, so that's why I'm using it here. I'm also using it, so I will be using this for editing, and I have already used it also for producing an annotated HTML file by this button publish, which I will also show, and on which I will be actually discussing the script. In order to run it in Octave, you have to have Octave on, so this is Octave now. You have to be in the directory where the script resides. So in my case, this is directory Octave. I make ls, which is listing everything that is in there, and our script is this one called sen level.m. So you can open that file using any editor, and in that case I'm actually using MATLAB editor. Here's the file, and here's the content of that file. So I said I produced some HTML from it, and on that HTML we will discuss the functions of that script before we start it. So here is the HTML produced directly from the code. So it's about evolution of an n-level system in wavefunction approach. We will first, this is also meant to be an introduction into a little introduction into Octave or MATLAB. So here's the code. So this first line means just I'm cleaning everything. Here is some switch to values 1 and 2, by which I will specify whether I want to work in site basis or eigen state basis. This thing also says hello before it starts, and of course here are the in this annotated HTML there's always an output of any specific part. So this says hello here. Here we specify the Hamiltonian. We'll be talking about just a 3-level system, and you can change anything that is here. You can make the matrix bigger, smaller, whatever you want. So I have here a matrix on which on the diagonal I have some energy. So one of the energy is 1.1 in some units, the other energy is 1, the last energy is 0.9. I specify them either through variables like that or directly into the matrix. So this matrix represents the Hamiltonian of the problem, and here I specify the initial wave function. So I first, because I assume that you can change this Hamiltonian here, the size of the matrix and so on, I take the size of the Hamiltonian and I create a vector with zeros which has the same size as the Hamiltonian. This is n by n matrix, and this is a vector of the length n. And then I specify the initial condition. Here this initial condition is such that the site 1 or the state 1 is completely populated. The initial condition that you specify here has to be normalized, or it doesn't have to be normalized, but then you will suffer from a problem that the output will not be normalized. Okay, so here I specify, down here I specify which basis I want to use. I will use site basis in this, or here in this particular version of the script I use site basis. You can change this. Then I have to specify the time evolution, that is time scale. I have to specify for how long I want to propagate. So I want to take 100 time steps with dt of 1, and this is, you can understand as femtoseconds, but of course the units are such that this is not precisely femtosecond. Here's the vector which contains all the times. So it starts at 0, step is dt, and it goes to nt minus 1 by dt, which means there will be really precisely nt steps. So next part is just for your information, when you run the script, it outputs the Hamiltonian. It makes the transformation into diagonal basis. We've discussed that all in other videos. So this here specifies or gets for me the eigen values in a matrix. This is the transformation matrix. This is its inverse. So here I put the eigen energies into a specific vector. Here I display the transformation matrix, and here I verify that transformation is correct. That is, taking s to the power of -1 hs, this has to get the diagonalized Hamiltonian. The output is here. The output is here. So this is the Hamiltonian. This is the these are the eigen energies. This is the transformation matrix, and here you see the diagonal Hamiltonian has these eigen energies on the diagonal. Perfect. All right. So now we'll be calculating the evolution operator, because we want to calculate the dynamics of the system. The evolution operator is defined this way, also discussed in some video, and we will calculate an evolution operator which will take us by one dt step farther. So I create a matrix n by n which is filled with zeros, and then I go along its diagonal, because we work in the diagonal basis here. I mean, regardless of whether I have chosen before to output things in diagonal, or that is eigenstate or side basis, I am always working here at this point with the in the diagonal representation. So on the diagonal I put e to the power of -I energy dt. H bar was set to 1 here. Now I choose whether I want to output in side basis or not. So if I choose side basis, then I have to transform that du matrix, du evolution operator, back to the side basis, which I do by means of this transformation. This was also discussed in the in a video. And if I don't, then I have to specify, I have to turn at least so this means I will be working in the diagonal basis. I would have to put my initial condition into the diagonal basis. So this is also done by the means of the matrix S. This is because I assume that the initial condition is specified in the side basis, that it is defined for the sites in space. Okay, now we will propagate the wave function. Here is a little problem, which is the problem of Octave, because I don't have any easy way how to distinguish the standing vectors or lying vectors. So sometimes I have to actually manually change it from standing to lying and so on. So this is done by putting an apostrophe behind the vector. So here, to calculate the next step of the psi, I need the last step, the step before. I want to propagate it by du, so this is a matrix multiplication, but somehow before I do that I have to change this vector from lying to standing and then put it back to lying. Apparently this definition simply gives me a lying vector, which is not what I want. Well, this doesn't matter. The important thing is here that the next step I get simply by multiplication of the previous state vector by the evolution operator, and that's how evolution operator works. It multiplies the state vector and changes it into the state vector in the future. All right, so now I calculate the populations, and the populations are calculated, well, they are obviously dependent on the basis in which we are. So if we are in the side basis, these psi t at specific times, the time is run by the index I, are the site values, probabilities, or this square, as you can see, this is psi conjugated, multiplied in scalar product with the other psi, and then there is an absolute value of that. So this calculates the probability of finding the system at site k here at time specified by the index I, and this is either in the side basis or the diagonal basis, depending on what I have chosen to work in. Okay, and at the end here I just plot the result. The plotting is done so that I first specify colors of the lines. Color is a third argument here, and it's a string, so it's basically an array of characters. And I plot always the population at time e, and I plot the population of the site E or state E, and I plot the sort of whole array of it at all times. This is it. Hold on just means that I'm adding the next plotting goes into the same graph. So here I plot all the states and their dependency. So with the initial values that we had specified at the beginning, we start from the population equal 1 on site 1, which is the black line. Then there is the red line and blue line, and these are the populations. So this way they oscillate for the parameters of the Hamiltonian we have specified. Okay, so this is sort of a description of what the script is, but if I want to run the script, I have to go to the Octave, and I would just type SEN level without the .m. That's an extension which is supposed to be the MATLAB files, and now the stuff runs. So it says hello, it writes out the output, and it creates this nice picture which I can move into our video, which is the picture that you have seen at the end of that HTML of the script. So I close this video, and I can now edit with my MATLAB editor. You can use any text editor. I will edit the input files. So for example, here I'll change this energy, which is equal to 0.9 to, let's say, 1.2. Save it, and I go to Octave, and now run, and I get a completely different picture. Just by changing the energy landscape, I have got a completely different picture. But as you could expect from quantum mechanics of closed quantum systems, this picture will repeat until the infinity. So there are some oscillations here, but there's a repeating picture for the infinity of time. We can also change the initial condition a little bit. Let's have a look. The initial condition was specified. It's specified here, and we had only the one, the site 1 populated. So let's now say we have equally populated sites 1 and 2, which means that both of the 1 and 2 have to have the value of 1 divided by square root of 2, because out of such vector I get normalized output. So I save it again, I go to the Octave, and I run the script, and here the picture becomes yet different. So I start with the population of 1/2 on the site 1 and 2, and then they are all coupled to the site 3 and to each other, and the population goes back and forth between all of them. One interesting thing is that very rarely you can see that, let's say, so we started from 1 and 2, and they, the population never gets completely to the 3. These things are actually quite common, and they are a reflection of the fact that the evolution of the populations in the eigenstates is such that they don't change. The populations of the eigenstate don't change. That means if I have somehow distributed my sites in the population in those delocalized states, and one of the states, well, their population is constant, and that state has certain proportion on some states, well, it simply cannot happen that all that population from that state leaves away. It cannot. There has to be at least a part still left there. So all this evolution inside bases is basically driven by the evolution of coherences. We can also try with this script another thing. We can have a look at the same system in the eigenstate basis. So here's our possibility to change the basis. So if I just put here Eigen and save it, then the same dynamics will be expressed. In the eigenstate basis. So let me run everything, and in fact here it is. The populations of all the eigenstates is perfectly constant in a closed system. So that was it. You can play now with the script. You can change it any way you want, of course, so that it is meaningful, and you can get some feeling about how in a closed system of several coupled levels, how the wave function or how the probabilities of finding the system at different sites, how it evolves.